In Scilab, you can very easily calculate the Routh table for a linear time invariant system using the built-in macro Routh_T. Imagine you have a system whose characteristic polynomial is as depicted in this slide. So all you have to do to calculate the corresponding Routh table in Scilab is first define S as a polynomial variable, and then you have to define the polynomial itself in terms of the variable, the characteristic polynomial. So if P is the characteristic polynomial, then you can simply call the Routh_T function and pass in the polynomial, and it will generate the Routh table for you. And from that, you can pretty easily understand that the system, the closed loop system, will have 1, 2, 3 and 4 poles on the left half plane, because there are 4 sign changes in the first column of the Routh table. So from plus to minus, minus to plus, and then again plus to minus and minus to plus. You can even verify this fact by calling the roots function in Scilab to directly calculate the roots of the polynomial that you have here. So as you can see, there obviously are 4 poles in the right half plane for the system. Similarly, if you have the forward path transfer function of a system as well as the feedback transfer function, and you have to calculate the value or the range of the gain k for which the system is stable, then you have to do the following. Since you have already defined S as a transfer function variable, you have to define the forward path transfer function G. This was your forward path transfer function. And then you would have to define the feedback path transfer function, which is H. Now keep in mind that if the system is a unity feedback system, in that case H will simply be equal to 1. And then you can calculate the Routh table in terms of the polynomial variable k like this. You would have to pass in G into H as a transfer function, and you have to define k as the polynomial variable. So this is how it generates the Routh table here. So these are rationals. This is 1 by 1, this is 11 by 1, this is 320 plus k by 11, and so on. Now you can try out this for different kinds of systems. Thank you.